just a quick recap. Okay, last time I said, okay, this is a D block element. These are not transition metals. Most of them are, but there are a lot of exceptions. जिसमें zinc और scandium ये हमने किया था. I said के D block elements के अंदर the ones that exhibit properties which are given over here, they're the ones that are transition metals. So not all of them form colored compounds. Not all of them have variable oxidation states. Zinc and scandium were one example. So transition metals were any D block element that can form stable ions which have an incomplete d subshell. So it's not the electronic configuration of their atoms, it's their ions. Their ions must have these incomplete d subshells. That was one thing. Up here we started off with the melting point metallic bonding part, which is no longer in the syllabus. So that's not there, but we can kind of वो उसी के साथ link कर दो कि melting point or catalyst के साथ. So this one, I told you that transition metals, I said that you got stronger metallic bonds if the positive charge, you got more positive charge and you've got a smaller ion, which basically means your charge density is really high and you got more delocalized electrons. So transition metals have higher melting and boiling points because of both things. They've got greater charge density, plus they've got more delocalized electrons. So this thing, we can also link this up with being good catalysts. I'm going to discuss why are transition metal ions smaller in size compared to these other ones, potassium and calcium, the ones that come right before them. So, or basically, why do they have greater charge density? Why is iron so small in size, and why is calcium, even though the difference is not that much, this is 20 electrons, this is 26, so difference is not that much. So the reason is, okay, let me add, why do they have smaller ion in size? Or we can also state, why do they have greater charge density?
Excuse me, sir.
Yes.
What's not in the syllabus? Can you repeat that again?
This thing, I think we discussed this. I mean, the new one was that melting points and boiling points are no longer in the syllabus, like in the October-November exam that was just given.
Oh, so I don't need to practice that?
What I think is that metallic bonding is part of the syllabus, right? I mean, you should know what metallic bonds are, right? So, yeah. We can still study this. We can study the density part and the melting boiling point part quickly, but these things are also linked with them being good catalyst. So all of the things that we study right now, like them having greater charge density, we can connect that with the catalyst part. Okay, so I think we should not totally just not study this, because I mean the basic concept behind this is also useful in other parts as well, right? So we're going to study this thing, that why do they have greater charge density and why the size of the ions are smaller. So there's a simple reason, like if you compare it with calcium is a bigger ion. So if you compare it with calcium, calcium's electronic configuration is 1s2, like it's got 1s2, 2s2, 2p6, 3s2, 3p6, and then it's 4s2. The 3D is empty. There is no electron in the 3D. So you don't basically write 3D. The reason I'm writing 3D is just to show that it's empty. Compare this with the iron. Iron's got 26 electrons. This one has 20. This one has 26 electrons. So the point we're trying to make here is same thing. 3s2, 3p6. The 4s is filled further. Then you have 3d6. Now, look at both atoms' electronic configurations. It's exactly the same electronic configuration. They have exactly the same number of shells or subshells. So they have exactly the same number of subshells, identical. The only difference is that iron obviously has more electrons, so the subshells are the same. Not only does it have more electrons, it's got more protons in its nucleus. So there are more protons in the nucleus. So there's obviously greater nuclear charge, more attraction for electrons. So basically the idea is they have, both of them have exactly the same number of subshells, the same number of subshells. Calcium has 20 protons in its nucleus, while iron has 26 protons in its nucleus. So the electrons are more strongly attracted, which is why it's smaller in size. So that's the simple explanation why iron, even when they form ions, they still have identical electronic configurations. I mean, they have exactly the same number of, they still have exactly the same number of subshells, but iron having more protons, which basically results in a greater charge density. So calcium being +2 and iron being +2. I mean, this one is Fe, this one is Ca. So which is why it's going to be smaller. So there's more attraction for electrons, and that's the simple explanation for that. Is this point clear?
Yes, sir.
Yes, sir.
So that's the simple explanation, that why is iron smaller in size? Which is why the melting boiling points would be higher as well, because the ions are going to be closer to each other. The second thing I told you, was talking about, was that you're going to get stronger metallic bonds if you have more delocalized electrons, right? So the second thing is that iron also has more. So iron also has more delocalized electrons, and the reason for that is that the reason for iron having more delocalized electrons. Now look at calcium. Calcium can only lose just 2 electrons. That's it. I mean, it can only lose the 4s electrons, right? Losing the next electrons is very difficult. There's a huge gap in the ionization energies. Like, you have to go all the way inside the subshell into a 3p6 to pull an electron out. So there's this very large gap, which is why calcium loses the first 2 electrons very easily, but then the next electrons are like really inside or close to the nucleus. In the case of iron, you've got the 4s, and you also have at the same time the 3d, which has electrons in it. Now the 4s and the 3d are known to have very little difference. Like the 3d and the 4s orbitals, subshells, are almost having, I mean, they almost have very similar energy levels. So what happens is that Fe can lose electrons. Fe can definitely lose electrons from the outer 4s subshell, but it can also lose electrons from the inner 3d subshell. As there is very little energy gap. So they have a very tiny energy gap. The 3D and the 4s subshells are almost energy-wise, they're very, very similar. So which is why iron has a lot more electrons to offer. So iron can therefore have variable oxidation states as well. It can form Fe3+. So the outer 4s electrons can be lost, but electrons from the 3D can also be lost. Calcium did not have that. Calcium's other electrons were like really far away, inside or close to the nucleus. So which is why they also have variable oxidation states. So this leads to variable oxidation states, but it also leads to more delocalized electrons in the metallic lattice. So Fe can be 2+, Fe can also be 3+. It can even be 4+, so it could have many. So it depends on the other atom. How many electrons is it able to pull? Because remember, an atom does not lose electrons on its own. There must be something else that must be gaining electrons. So it depends on the other one, the one that is the oxidizing agent, that how many electrons can it pull out of the 3D subshell. So which is why you have variable oxidation states. You do a lot of titrations where Fe is getting oxidized. So so that's the reason why they have multiple oxidation states. Is this point clear?
Yes, sir.
Yes, sir.
So we've covered two things in this. One is, why do they have smaller ions? Why do they have greater charge density? You've got more protons. So there's obviously more attraction for electrons compared to group 1 or 2 metals. And the other one is they've got more delocalized electrons. They can lose more electrons and they can have multiple oxidation states as well. So they have variable oxidation state. We're done with that. We're going to focus on them having them behaving as catalysts. So why are they really good catalysts? And we're going to come back to these two things. So why are transition metals really good catalysts? So let's focus on that. And in this, we're going to study two, 3 examples as well. As I did, I'll have to search that because I just remember, I mean, this October exam, they were following the previous syllabus. So I'll probably keep the syllabus open because now the new syllabus is now basically going to be the one that we'll study. So we'll just keep it open to see if we miss
Sir?
anything. Yes.
There are 6 electrons in the 3D subshell of iron, right? So
Yes.
why have we only seen Fe2 plus and Fe3 plus? Why not Fe4 plus or 5 plus or some other things?
Nahi hota. I mean, it's I mean, look at iron oxidation states. Fe2 plus and 3 plus are the common ones. Okay. So I mean, you can see, I mean, this is you can even get +7, +6. I mean, ignore this. I'm just talking about the stable ones. This one, +2, +3, +4, and +6. So you can have multiple oxidation states. The thing is, an atom is not going to lose electrons on its own. I mean, the easiest oxidation state is usually +2 for a transition metal. I mean, most transition metals that you've seen, they would always have a +2 oxidation state. Why? Because the 2 electrons from the 4s would be lost, right? So copper is +2, nickel is +2. A lot of them are +2. Iron is +2, chromium is +2. So Basga, it depends on the other atom's ability to pull electron out of it. Do you get my point? Like you got iron 2 plus, you reacted with KMnO4. KMnO4 is going to oxidize it, and it's going to pull one more electron out of the 3D as well. So usually higher oxidation states are kind of slightly more difficult to form, but they can form. Okay, so iron does have multiple oxidation states. Most of the time we just see 2+ and 3+. So coming back to the catalyst part. Okay, so we're going to link it up with what we've just studied. So they're really good catalysts. And we'll do a couple of examples. I mean, it's iron in the Haber process. You got V2O5 in the contact process. So you got V2O5 in the contact process, and then you have a nickel in the hydrogenation of alkenes. And let me just quickly search in the new syllabus the detail about this. Just 1 second. You can explain the activation energy, Boltzmann distribution, reaction. That's fine. Explain the reaction is different, one lower. You get this one. Describe the action. Iron in the Haber process, rhodium in the catalytic removal oxides of nitrogen from the fine. Describe the mode of action of homogeneous catalyst. Fe2 plus and this thing. Okay, that's fine. So we will study all of this. Okay, that's written somewhere else, but we'll connect it with this one. So good catalyst. Nickel in hydrogenation. So we'll do the other examples. So the first thing is, why are they good catalysts? There are two reasons for that. One of the reasons is that if you look at how metals behave, you got potassium over here, 19 protons. You got calcium over here, which has 20 protons. You keep on moving to the right in the periodic table. Okay, so I'm in period number 4 and I'm moving to the right. So I'll meet all these other transition metals like Fe, 26 protons. Then you have cobalt, nickel, copper, etc., and so on. If I move to the extreme right, I've got bromine, which has 35 protons. So the transition metals are somewhere in the middle. That's why they use the word transition for them, because you're transitioning from one side to the other side. I mean, this side is your metal side. This other side is your non-metal side. Now, there is a change of behavior when you move from the left side towards the right side. Potassium tends to lose electrons. Metals really like to lose electrons, especially group 1. They like to lose electrons. These non-metals over here, they really like to gain electrons. So there's an obvious reason for that. And that reason is that why is bromine gaining those electrons so strongly? Why does it like to form negative ions? Because it's got more protons in its nucleus. So it's got more protons, and since it's got more protons, there's going to be greater attraction for electrons as well. So there's going to be more attraction for electrons. So why was group 1 so reactive? Why was it losing electrons? Because it's got fewer protons in its nucleus. They have the same number of shells, but since it has fewer protons, there is lesser attraction for electrons. Now, both sides are very reactive. I mean, this side is reactive. I mean, they're kind of reactive. They're actually very reactive. Why? Because they're always trying to lose electrons. This other side is also very reactive. As nonmetals, they're always trying to gain electrons. I mean, is this point clear? The two sides? Yes or no? Is this clear, Bhaskar?
Yes, sir.
Okay, Baki, Zoha, is this clear? Sam, is this clear?
Yes, sir. Yes, sir.
Achha, so you've got these two sides, and then you're stuck with the transition metals that are right in the middle. Transition metals tend to be unreactive. Basically, they're kind of somewhere in the middle. They're kind of somewhere in the middle. You move to the right, you got more protons. So they actually have a very small or lesser tendency to actually lose electrons. Like I mean, we've all seen iron. Iron has got 26 protons. Usually, iron is not very reactive. I mean, you make things out of iron. I mean, a car is made out of steel. You don't see the steel reacting, like at least not for 20 years. So iron turning into ions and losing electrons, that is not a very fast process. They don't really like to lose electrons. So they hold on to the electrons very, very strongly. So so basically when you're moving to the right, what is happening is that they're losing the tendency to actually lose electrons. And instead they develop, because of the higher protons, they have a very small tendency to actually attract electrons. So they won't be gaining electrons, but they would be holding on to the electrons really strongly because they've got more protons. You keep moving to the right, you become a non-metal. You got more protons, so now you can safely gain electrons. So is this idea clear about transition metals, that they don't really like to lose electrons? They hold on to the electrons very strongly because of the greater protons, greater positive charge in the nucleus. So they don't really like to lose electrons. At the same time, they develop this very small tendency to actually attract electrons. So is this point clear?
Yes.
Okay, so basically we can sum that up as transition metal ions having a greater charge density. Now, there are two ways that transition metals act as catalyst, and why the elements on the right side or on the left side are not able to act as catalyst. The first problem with the elements on the left side is they will react. I mean, they're very reactive. They would immediately lose electrons. They like to really, really lose electrons. So they won't be able to act as catalysts because they're going to take part in the reaction. They're not going to sit around. Same with the elements on the right side. They would try their level best to gain electrons. So they're not going to just sit around and let the other reactants react. They would actively take part in the reaction. Transition metals are not actually interested in the reaction in the first place. So how do they act as catalyst? Let me just sum this up. This thing, let me write the main point. More protons, smaller ion. In the metallic lattice. So they have greater charge density. which is why they have a weak attraction for electrons. Not a strong one, but a weak one. So they're not going to form negative ions or such. So let's see how, and let's be very specific. Let's just follow the syllabus. So he's asking for iron in the Haber process. So let's go with iron. Actually, the other one would be exactly the same. Palladium or platinum or rhodium in the catalytic converter, or removal of oxides of nitrogen from the exhaust gases of car engines. I'll just write down the reactions, but one example would be sufficient because the other one would be exactly the same. So the first one is, how does it act as a heterogeneous catalyst? And the way it's going to do that is, so what is a heterogeneous catalyst? That's the first thing. So when the catalyst and the reactants have different phases, so when the catalyst and the reactants have a different phase, that is a heterogeneous catalyst. So iron in the Haber process is a prime example. You've got nitrogen, which is a gas. You've got hydrogen, which is also a gas, and together they're turning into ammonia, 2 molecules of ammonia, and that is also a gas. So all of them are gases. Just a second. So all of them are gases, while iron as a catalyst is a solid. So how does iron break the bond? Remember what a catalyst does. Catalyst lowers the activation energy. The problem is, in this particular question, in this particular reaction, the problem is that the nitrogen triple bond in the N2 molecule is really, really strong. So it's very hard to actually break the triple bond. So what you have to do is you would have to sort of collide them together with a very large kinetic energy, so that the old bonds get broken. So it's hard to break the old bonds. Which basically means that they've got very high activation energy. Large amounts of kinetic energy are needed so that the molecules, they really bump into each other, collide with each other, and the force of attraction, the force of collision is able to break the bonds. So high activation energy is needed to break those old bonds. So it's all, and it's not the HH bond actually, it's the triple bond that is really, really strong. So you need to give them kinetic energy. So what does iron do? When you introduce iron to this, so now here's the iron catalyst. So remember what we just discussed. Like if I can just copy paste the metallic bonds that we drew earlier, I'll just copy paste that. And I told you that they've got really high charge density. They've got a lot of protons here. So here is So anyways, here is my Fe catalyst. It's metallic lattice. Let's say there's small pieces of granulated iron that have been added over here, and they've got really high charge density, 26 protons in the nucleus, and they've developed this weak attraction for electrons. So here's your N triple bond N that's roaming around, flying around the catalyst. And here's your H2 molecule that's also flying around very close to the catalyst. And so this one is flying around with some kinetic energy. This one is also moving around and bumping with the catalyst molecules with some kinetic energy. What will happen is that iron, being a transition metal, and because of its greater number of protons, it starts to pull those electrons very, very slowly in the triple bond. And remember, there's 6 electrons over there. So if this N2 molecule comes sufficiently close to this and bumps or collides with it, the electrons over here, they get pulled towards the catalyst. Same goes over here. The 2 electrons over here, they eventually get pulled or get attracted to the catalyst. Eventually, what will happen in the next step is, adsorption is going to happen. So adsorption is the process where the reactant molecules, they end up forming these weak bonds with the catalyst. So the triple bond, or the 6 electrons that were present between them, those electrons, they get pulled towards the iron catalyst because the iron is weakly attracting them. And remember that it's weakly attracting them. So it's not really forming a very strong bond. It's just a very weak bond that is formed between the nitrogen atoms and the catalyst. Same goes for hydrogen. Hydrogen had electrons right in the middle, but those electrons are going to get pulled towards the catalyst. Is this point clear?
Yes, sir.
So that's known as adsorption. इसको explain कर लेते हैं कि अच्छा, so this is the reactant molecules weakly bond with the catalyst. Achha, if it had been a non-metal, what would have happened is that the non-metal would have taken those electrons and made very, very strong bonds. So transition metals they have the right attractive force, which is a weak force. So they've weakly bond with the catalyst, which weakens their old bonds. So the next step is, remember these atoms and these molecules, they've got some kinetic energy. So they're flying around. So the bonds are very weak. So they're not going to just stick there forever. The bonds are eventually going to break. Okay, so the atoms have some tiny amount of kinetic energy, which would be enough. You don't have to apply a lot of force. These weak bonds would break anyways. And when they break, the result would be, so the weak bonds have broken now. The nitrogen atoms are now just flying on their own. And the iron, they're no longer attached to the iron. But the good thing is that all the old bonds are broken. So iron, in a way, helped or provided some of the activation energy that was needed to break those bonds. So you don't have to give them energy. Iron helped you along, and it helped us in breaking the triple bond. So now new bonds can be formed. So this is known as deadsorption. So deadsorption is that the old bonds or the weak bonds between the catalyst and the reactants, they eventually break. And now new bonds can be formed. So new bonds can be formed now. So is this clear?
Sir, those electrons, so now iron has those electrons, nitrogen and hydrogen.
See, nitrogen took it back. Remember, iron is not it's not strongly attracting those electrons in the first place. So iron is never going to gain those electrons. Do you get my point?
Yes, okay.
Okay. So, I mean, if nitrogen atom has just a tiny bit of kinetic energy, it would eventually fly off and the bonds will eventually get broken. So nitrogen keeps its electrons, but the electrons are no longer bonded between the two nitrogen atoms. Okay? Is that clear?
Yes.
So, let's continue with the whole catalyst thing. Okay, we did the first part. We're going to discuss homogeneous in the next class then. Okay? So, okay, take care.
Allah Hafiz.
Hafiz.